Okay. Hello everybody. Welcome to today's Rubin Science Assembly. Um, I'm Jeff Carlin. I'm a member of the Rubin Community Science team. Um, and I will kick us off today. We are going to talk about the new survey strategy simulations, version 5.3. But before we get to that, I have a few announcements, and then I will hand it over to today's presenters. We have, as always, you can check for news on our website at rubinobservatory.org. There's a for scientists section where you will see announcements like that alerts have been flowing since February, for example. Our founding director, Tony Tyson, was included in the Time 100, um, which was a great fun story and a great honor for Tony. Well deserved. Um, there are lots of announcements today, actually, including coming up very soon is the Rubin Data Academy. Look for an announcement on the community forum and in your email inbox probably later today, as soon as I get around to actually sending that. Anyway, the Data Academy is meant as a week-long intensive sort of boot camp to get you up and running with the Rubin data products and our tools. So if you are somewhat new, or even if you just want a refresher, if you have seen everything but you want a little bit of a refresher, this is a great time to sort of condense into 1 week to sort of get up to speed with how to use the data. We also have our annual community workshop coming up in July. Um, there is in-person participation, but it is restricted to 250 people, and we're nearing that limit. So if you're interested, do get yourself on the wait list right away. And of course, there is hybrid uh, attendance as well. So do register if you intend to tune in online. So coming up next week's Science Assembly, Yumi Choi will tell us all about the extendedness parameters, how to identify stars versus galaxies, resolved versus unresolved sources, um, with the parameters that are in our catalogs. The following week, we have a special session on early science with Leanne Guy. That was originally scheduled for a couple of weeks ago, but we had to reschedule it. So do check that out. Leanne will tell you all about the data that will become available in the near future. Uh, Also wanted to mention these upcoming meetings. There is this meeting, Rubin 2036, happening at SLAC in Northern California. Um, the registration deadline was just extended and ends today. So if you're interested, do register. And I know there is some travel funding for early career scientists if you're interested in that event. Um, LSST at Europe and LSST Latin America are also coming up later this year. The information is here, and I'll make sure I share a link to the slides very soon. Um, excuse me. Relevant to today's discussion, the Survey Cadence virtual workshop is coming up starting next week, and it's spread over 3 days, the 10th, 11th, and 15th. Do you see the website that is linked here if you are interested, and you will probably hear more about that in just a few minutes. Also, there is funding available from the LSST Discovery Alliance for to fund workshops, hack days, things like that. So do check out that call for proposal if you are interested in organizing an event. Especially focused on the upcoming Data Preview 2 and Prompt Data Products releases. Also, if you're interested in a job working on the Rubin project, data management is hiring a couple of research scientists in the algorithms and pipelines group at University of Washington. So do check that out as well if you're a software developer and would like to work for Rubin. As always, I would like we like to remind you that um, there is a users committee that represents you to the Rubin project. So they're charged with taking feedback from you about our data products and the science platform, um, and sort of feeding that back into recommendations to the Rubin directorate. So we list those folks here, and they're always happy to hear from you, um, either via email or the community forum. So do reach out if you have any comments, questions, or even just compliments to share. Also like to remind you that the Link Frameworks team holds office hours most Thursdays in the hour immediately following this. Um, and if you're not familiar, Link builds a variety of tooling to help facilitate use of the LSST data products. Okay, and so now on to the main attraction today, which is discussion of the new simulated survey strategy version 5.3 that was recently made public. I think today we are going to hear first from Federica Bianco, who is the lead of the Survey Cadence Optimization Committee, and then we will hear from Lynn Jones about the actual new survey simulations. And I think we can just go ahead and pass it on to Fed.
Yeah, I just sent you a request for screen sharing. Can you enable it, please?
Oh, yes. Let me see. Where did it appear?
I think I'm host, so it came to me and I just clicked allow.
Thank you.
Oh, excellent. Okay.
And as usual, because these are Google Slides so that you can access them later when we give you the link, I will not see you as I present. As soon as I click on slideshow, I will not really be able to see any of you. So please, if you have questions at any point, do indeed interrupt me as you wish. My name is Federica Bianco. My pronouns are she, her. I'm LSST survey scientist. And we're here to tell you about the new simulations of the survey version 5.3. Obviously, for inclusiveness, I will want to make sure that everybody is aware of the process of how Rubin designs the survey strategy, which is rather unique, and specifically, it's uniquely community focused. So I will give you an introduction to this process, and then I will pass it on to Lynn Jones to tell you about the specific newest simulations of the survey strategy and how they inform you about what you can expect from LSST. So the story of how we designed the survey strategy dates way back, approaching 20 years at this point, in the LSST science book. So that's the year 2009, before I got involved in LSST, before probably a lot of people here got involved in LSST. There was a tentative survey strategy, which you see at the top as what you see here is the footprint that was designed at the time, and the number of images that you would take on each element of the footprint. This sort of, I'm going to call it naive, with no offense to our early directors and our early teams. This was a naive sort of straw person plan for how Rubin will observe the sky, but the intent was that LSST, quoting from the book, the LSST system can adopt a highly efficient survey strategy where a single data set serves most science programs. One can think of this as massively parallel astrophysics, and this is a survey for everyone. A vigorous and systematic research effort is underway to explore the enormously large parameter space of possible survey cadence using the Operation Simulator tool. That process, which is described here as vigorous and systematic, is still ongoing and will continue throughout the survey. The survey design is designed to be responsive to changes of scientific priorities, changes of environment and performance, and designed to enable a flexible survey, which also will be consistently trying to achieve the stated goals of LSST, the four science pillars and beyond. Okay, slides are already not showing quite. Okay, I forgot I had an animation here. So one may think of, if we had this enormous parameter space and we need to decide what to do, one may think of engaging in a fairly competitive process of establishing whose scientific priorities are most valuable and following those in a sort of hierarchical way. You can think of this as a cadence war, if you wish, but we don't like wars. In wars, some people lose everything. Every individual loses something. Together, we lose our togetherness. So LSST did not want to engage in war. It wanted to engage in a process that is collaborative and cooperative and that involves the entire LSST community and the entire scientific community. So that's what we did. Before I go on, I have a quick Slido for you. So I would like you to grab this QR code or go on slido.com and use this code. I will ask you a few questions to get a sense of how familiar you are with the survey strategy design process for LSST. Obviously, the answers are anonymous, and we will look together at what the answers are as I get out of here and go to Slido. So can you please click on the QR code or grab the code here and start answering this question. Have you interacted with the SCOC or attended any of the SCOC workshop or Rubin CW sessions? That's pretty cool. I'm gonna give you another 10 seconds. I see about a half of the people have answers. I have more questions, so I will just move on to the next one in a couple of minutes. So it's pretty much a mix, right? So I will explain to you what the SCOC is, and I hope that this discussion will give you opportunities to then in the future engage with the SCOC if you have not done that yet. If you don't know what the SCOC is, please hold on. I promise I will tell you. Next question is, have you ever tried to create an observing strategy metric in the math framework? So again, pretty mixed. If you answer what on earth are you talking about, please stick with us and I will tell you. Let's move on to the last question. Have you seen the most recent OPSIM released as version 5.3 on communitylsst.org? Thank you for participating. This gives me a sense of not only the temperature of the room, but also it does help me understand how well we have socialized all these concepts. So going back to my slides. So as I mentioned, we were designing a process by which we could optimize the survey strategy based on scientific expected throughput of the survey across multiple science cases. And we needed tools to enable community interaction if we wanted this to be a community-centered approach. So the chief tools that were built primarily by Peter Joachim and Lynn Jones, who are still here as survey strategy scientists, and Lynn will talk to you in a second, are basically a simulator that simulates a database of LSST observation as performed by the scheduler which is automated and follows criteria that are established to determine how the survey should work to pursue specific goals. So it includes weather patterns. Well, it includes weather considerations. It includes visibility pattern, lunation, and then science-driven choices of how, for example, you alternate the 6 filters of the LSST or where are you going to observe next. So what you see on the left of this diagram is essentially this database being built. Where did LSST observe, with which filter, at which point in time, and also you get information such as what was the magnitude limit of that observation, what was the brightness in the background, etc. So that's the pillar. Again, it doesn't simulate images, it simulates a database of observations and observation information. And then we have the metric analysis framework, which is a Python wrapper by which you can code up the science throughput of a specific database realized by an OpSim to see how well it would do your science. For example, if your science depends on having a large footprint, you may see how the footprint evolves over time, and you may come up with a metric that, based on the size of the footprint over time, measure your ability to do science. If your metric depends on measuring variability of stars on certain timescales, you can grab the time gaps between the observations in certain filters and how the observations are distributed, what we call the cadence, and you can measure how well that expected cadence would lead a science throughput for your specific science. So those are the tools that were built to engage the community in this process. And the process began, the systematic process of exploring the potential survey strategy parameter space began roughly in 2014 with the construction of these 2 pieces of software and with the engagement of a somewhat restricted group of people led by Phil Marshall, mostly people that were in science collaborations and quite engaged in the science collaboration, that first explored a set of 16 simulations and built the first set of metrics, maths, to evaluate their scientific throughput. And it became immediately obvious that there wasn't enough people, there weren't enough experts, there wasn't enough diversity of expertise in the room, not enough voices were being heard, and not enough simulations were being produced. Many versions of the OpSim later, we can produce simulations much faster than we could then. So the Science Advisory Committee advocated for executing a systematic effort to further improve the LSST cadence, which continue with open calls for community contributions. In 2018, we received 48 community white papers. These included hundreds of scientists, so we massively expanded the number of people that were interacting with the system to provide survey cadence recommendations. And we instituted the Survey Cadence Optimization Committee. That's the first riddle that I asked you earlier, the SCOC, Survey Cadence Optimization Committee, which I now chair. It's a community committee that is tasked with soliciting, collecting, and aggregating the input from the science community about the survey strategy's performance and design optimal survey strategies with a science-driven, in a science-driven fashion. We didn't stop there. This is the current composition of the SCOC, and you can read about the SCOC at the link that I have in these slides. The SCOC is I guess I mentioned community, is stacked by community members. Lynn Jones and myself are non-voting members ex officio. Eric Bell, we typically have one Rubin data management person on the committee that provides double expertise on science as well as an insight in the committee, in the data management operations. And the members are selected to be comprehensively knowledgeable about all possible science aspects, all possible sciences that LSST will pursue. And they also serve as liaisons into the science collaboration. Mind you, not as advocates for a specific science, even if they are liaisoning with the science collaboration that does a specific science, but their goal is to provide an overall optimization of the survey strategy, not to advocate for a science goal, but to share their expertise on that specific science aspect for sure. The Survey Cadence Optimization Committee produces survey cadence recommendations. Those recommendations are delivered to the director of the observatory, who decides ultimately what survey strategy to implement. We have three main recommendations. They're called phase 1, phase 2, and phase 2 and phase 3 recommendations. So 2022 was phase 1 after the first set of white paper. More white papers, more cadence notes in this case, 39, more people involved. Phase 2 recommendation in 2023, a lot more people involved, a lot more simulations done, hundreds of simulations, hundreds of maths at this point available. And phase 3 recommendation was the latest at the beginning of 2025. This was designed as the recommendation for the beginning of the survey strategy. But in 2025, when this recommendation was delivered, we still didn't have as sophisticated a knowledge of the system as we have now. So we envisioned it as subject to changes as we paid attention to the system performance. The process works by looking at scientific-driven metrics that you, the community, write through the math and looking at how they improve or damage, how a simulation improves or damages the performance on those metrics. So here is an example. You have a bunch of metrics on the y-axis. For example, solar system metrics at the top, TNOs, NEOs, specific populations, Likers for solar system objects. You have stellar metrics here, galaxy metrics here, and both galactic and number of galaxies. So LV dwarfs, number of galaxies, number of stellar objects, brown dwarfs, microlensing entering the time domain metrics, kilonova metrics, supernova metrics, and cosmological metrics such as weak lensing on 3.2 figure of merits, and then some metrics that are core science deliverables as written in the science requirement document for LSST, proper motion and parallax. In general, in plots like this, red means worse, blue means better by some fraction that you see here on the axis. In this particular rendition, the metrics range from 50% better to 50% worse. And always one of the simulations are on the x-axis, generally more recent simulations to the right and more older simulations on the left, specialized modifications of a given simulations are in blocks like this. And we always choose one simulation as the reference one. In this case, it was baseline 431. And so that gets assigned the value of 1 for all the metrics. So we can see comparatively, are we improving the science throughput or are we damaging the science throughput? You can also look at them as a line plot. To the right here, we do both. And really, it's a lot more complicated because that is a very selected subset of the metrics that the SCOC works. This is a more complete yet not complete list of the metrics that we look at. And all those metrics, most of those metrics anyways, were built by the community and delivered together with those cadence notes and white papers. They determine significant changes to the survey strategy. Most obviously, graphically, I can show that to you as how much the footprint has changed over time. On the left, you have the initial footprint. On the bottom right, you have the footprint as delivered in our phase 3 recommendation. Also, we provided opportunity for these papers, cadence notes and white papers, to be published as peer review papers on the special issue of the LSST supplement, the Astrophysical Journal supplement series. And we now have 30 papers that have been published based on this cadence work from the community as peer review work, and more are being accepted in this journal. Two key changes over time that I want to mention. In version 3 of the OPSIMS, we recommended to perform LSST with a rolling cadence. So on the right side here, you see the observations as they happen every night. On the left side, you see the cumulative observations. So basically how we proceed to build the stacks for LSST. Rolling refers to the fact that we alternate in different years regions of intense observing and less intense observing, the stripes that you see on the right side plot and that also co-add in the left side plot. That allows us to have a slightly more dense cadence on the on season, on the season where we're focusing on a particular area. Obviously, a less dense cadence on the other half of the sky, but overall, that has significant improvements for time domain science, as most of the naive cadence, take the 800 observations that LSST should take in 10 years and distribute them evenly over 10 years. And 6 filters, that would lead to 2 sparse cadence for most time domain science. Obviously, that also means that the uniformity of the coads is not always high. With some on alternating years, we had those stripes that show up in the coads, and that has consequences for cosmological measurements. So it's a balance between improving time domain science and improving uniformity. And another key change is the introduction of the Rubin Target of Opportunity program, which is now active and has already delivered at least 3 circulars with observations responding to gravitational waves and solar system triggers. And this has been designed entirely by the community primarily during a workshop in 2024 at Berkeley that designed the observations. It's a highly automated process for responding to gravitational wave and neutrino and solar system triggers. With a strategy that has been designed by the community and is implemented at the observatory within the scheduler, but also with the oversight of a human committee that continues to monitor the effectiveness of the program and of the strategy as designed. So this is all of my overview of the process of designing the survey strategy. And so with that, I can pass it on to Lynn.
Thanks, Finn. Okay, I put a link to my actual slides in the chat if you want to follow along. And let me get sharing set up. And Fed, we've gone a little bit longer than I think we had maybe originally planned. So let's I will go somewhat quickly through some of this. Here we go. Slide.
Yeah, but I think it's okay because we still have a full half hour.
Yeah. Okay. So as Fed said, now we are at these 5.3 simulations. And so this is building on that very long history of opsons and outputs that she had mentioned. Likewise, I'm going to say if you do have a question, please go ahead and let me know, and we can stop to address those as they come up. Okay, so v5.3 simulations, they were announced last week. I think that was last week, May 26th, and it's on community. The baseline v5.3 is what mostly I'm going to talk about here. And it is primarily an update to our previous baselines. And we're basically responding to what we've learned about what data management needs based on what we saw during commissioning in the SV survey and on what we've learned about SOMET operations from early operations and updated engineering schedules. So really, I just want to make sure we're clear, we're not reinventing the survey strategy from scratch here. This is an update based on what we're learning and what we've seen. If you have been following along with survey strategy, you may have seen v5.0 there, and you may have been saying, oh, we're at 5.3 now. What happened in between? So there were 5.1 and 5.2 sets of simulations. We didn't really announce these widely. They were more like works towards progress that we had, and we didn't really announce. They were available, but they were not ones that we made a big public announcement about. Okay, so as a reminder of the general LSST survey strategy, This is the part I'll go through very quickly because I think most people are somewhat familiar with this by now. If you're really not, there are more details at this website that's on the upper left there, survey-strategy.lsst.io. So we have the wide, fast, deep. That's about 80% of the survey visits. Visits are required in pairs, mostly in different band passes. After year one, the rolling cadence that Fed was just talking about starts and alternates different alternating declination rate regions so that we increase the cadence about half of the time.
Lynn, I
Yeah.
just wanted to let you know that we're not seeing your slides advancing.
Oh, sorry. Okay. Oh, you know what? Sorry, you are complete. I see. We have. Thanks for stopping me there.
Sure. Yeah, we see the screen share, but we just don't see we don't see them advancing.
Yeah.
I think you're sharing the wrong screen.
Oh, you know what? I think maybe what happened is once I put it in slideshow.
Yeah,
Yes.
exactly.
Yeah. Okay. Let me see how to fix that. Well, there we go. Okay. Way at the bottom of the list. Now, do you see it? And
Yes.
advance.
Yep.
Okay.
We see, wait, yeah, there we go. I saw
Okay,
them
good.
change.
So this is what I was talking about with the Wi-Fi steep. Luckily, you probably all had an idea in your mind what the Wi-Fi steep footprint looked like. So this is the bulk of our visits. Then we have the mini surveys, which have the North Ecliptic Spur, we call the NES, the Dusty Plain, that's the galactic plane outside the Wi-Fi steep region, and the South Celestial Pole. So each of these mini surveys can have its own filter balance. It's not the same over the entire sky, and they are aiming for some percent of the visits that we have completely. And I will point out here, the mini surveys and the White Fest Deep are balanced in terms of overall ratios of visits, not the specific numbers of visits. So, for example, if we lose 10% of our visits, that 10% loss is shared evenly or roughly evenly between the mini surveys and the White Fest Deep. All right, the sort of next category of surveys of things, how we observe on the sky are the deep drilling fields. So these are 5 independent deep drilling fields where there are actually 6 central pointings because EDFS is split into 2 so that it covers a wider area. And these are observed with a predefined sequence of visits with a predefined goal cadence. There we go. Get rid of those. Okay. Now the thing that was a little bit new around v5.0, and so this may be newer concept if you haven't been following along with the survey strategy, is that we used to have the DDFs sort of consistently acquiring visits over all 10 years of the survey. Because of needs around getting very high supernova and also needing to monitor things over longer time periods, we've actually split this so that each DDF has one or more for Cosmos deep season where there are very long sequences in the deep season period so that they get maybe 100 visits in a night. And over 50% of the DDF's visits are acquired in the deep season. And then the other years are all shallow seasons with short sequences. So this is a change that was introduced at v5.0, and we call this deep drilling strategy the ocean strategy. So it's like, because it's deep and shallow. It is essentially kind of like a rolling cadence in the deep drilling fields, but very extreme. And then the last sort of category of observations are the microsurveys. So these are small programs that require less than 1% of the survey time to execute. The SUC has currently approved a near sun twilight microsurvey to start running in year one, and that's the only microsurvey we're currently including in the simulations. The near sun twilight microsurvey runs with 15-second exposures. It's high air mass towards the sun, and there are quads of visits in the night in RI or Z. So these only execute during twilight, so sort of -12 to -20 or so sun altitude, and only every few days, not every day. The last other category are the target of opportunity observations. So Fed mentioned this. There's up to 3% of survey time may be directed to TOO follow-up, and the plans for follow-up are described in the workshop report. The Rubin TOO advisory board has been set up and provides guidance regarding specific TOO events. Okay, so that is my overview of where we have been for the survey strategy. All of that is still true in v5.3, but we took what we learned from commissioning and what we've learned from talking to the summit and having updated performance estimates, and we've cast that into what we have for the survey strategy in 5.3. So the changes in the strategy itself are in response to what we learned about data management needs, and primarily these focus around issues with chip gaps and coverage. So for the DDFs, in the SV survey, the DDFs were a little isolated and they didn't have wide fast deep coverage in the background. So the chip gaps that resulted from not dithering within a night were a big problem. As we're early in the survey still, and we don't have significant sort of background coverage, we anticipate that we still need to dither within the night for the DDFs. It is possible that later in the survey we may not need to do that, but most likely during the nights with the very deep sequences, we would probably still need to dither within the night, because otherwise we would have major chunks of the visits in the deep drilling fields that would have chip gaps that would stack at the same location. Okay, for template creation, this was the other big change. What we saw happening with template creation was not quite what we had expected prior to actually seeing it work. What we found was that and that we certainly had some uncertainty about it before, but now we were learning about what actually is required. So there were two things. There's requirements for image quality. This is in the full width half max and the transparency. And we knew about those, but what we hadn't anticipated is the difficulty of predicting what that cutoff would be before you actually have the images. And then also requiring that you get at least so many images that meet that quality. And then the second half of this is that because of the chip gaps again, the technical requirement was 95% pixel coverage of a patch, which is not the same thing, with 3 images. And that's not the same thing as getting 3 images with overlapping visits. So what we found is that it looks like we need to acquire 5 to 6 visits to overlap a given point in order to meet the pixel coverage requirements. So the end result of this was that we needed more images for the template tier, and the image quality requirements needed to drive our image acquisition a little bit more. And so as a result of this, we have set up a separate template tier set of surveys and we call this surveys. This is our survey objects inside this the scheduler. So we set up a separate template tier so that we can drive the acquisition of these visits more strongly. So the templates in v5.3 are programmed in pairs. That is new at 5.3, 5.1, and 5.2. We were still figuring out how to do that. And so in those intermediate simulations, the templates are single visits, but we figured out how to do templates in pairs. They're pairs not always in the same filter, but so the pairs not always in different filters, but sometimes like for you and you, they're the same band. But with this template here, we can't guarantee that we'll get enough images to get a template within year one, but we can guarantee we're aiming for that explicitly and trying very hard. Obviously, we can't guarantee anything about how, the coverage on this guy until we get those visits.
Lynn, I just wanted to pop in and say we have a hand raised with a question.
Oh, sorry. Yes, I don't have the
No worries.
images up, so please do.
Yeah, I just wanted to ask what is bad about having chip gaps for deep coads? More efficient to just go back to the exact same place, and you lose a % or two on chip gaps, but filling those costs you a lot more than the area that you gain.
Yeah, I think this is so at the point of when we were running the commissioning survey, there was two aspects here. One is that the visits we were acquiring okay, I'm going to take a couple steps back here. So when data management creates coads, they create what they call deep coads, which are the deep coads are what they use as the inputs to catalogs and that are used to generate the catalogs that people use. Then they have template coads, which are the ones which are used as the templates for difference imaging. The requirements about needing to have the pixel coverage definitely apply to the template coads. What I don't know is how strongly that applies to the deep coads. For the template coads, it makes a lot of sense because you need to have this image in the template and then be able to warp it to whatever image you acquired later, right? For the deep coads, it might be different, and I don't actually know the details on that. So your question, what is the problem with having chip gaps? For the template images, it's definitely a problem. And during commissioning, the deep drilling field observations, given that we didn't have previous observations of this part of the sky, were primarily like the viewpoint was these are for we need to generate templates for these areas. As for whether or not the chip gaps are a problem for deep coads, it's a good question, and I don't know because there could be some issues with calibration that I'm not appreciating, or other issues. But I think this is a place where we can go back and we can ask data management what happens if you have chip gaps in a deep coad, and is that really a problem? So maybe we don't need to dither during the deep seasons, for example. That said, I'm not sure if you had 100 images where you didn't dither. I'm going to guess that for low surface brightness and removing systematic effects for low surface brightness galaxies, that not dithering is going to be a problem. But this is also not something that I can answer right now. So
Okay, thanks. Yeah, it might be good to discuss this further.
yeah, but it is true that our camera does have a fair bit of scattered light. And it's getting better because not all of the scattered light mitigations were in place during commissioning. But it is definitely true that one of the reasons for adding more dithering was not just chip gaps, but also to be able to deal with the scattered light. And I'm sorry, I forgot to mention that earlier, but yeah.
Sorry, Rick, you mentioned Wi-Fi's deep should cover the chip gaps, but not to the depth of the deep drilling fields. So that the deep drilling fields are by definition 10 times deeper.
Right, but for calibration, would that be good enough? Do you have to go to the same depth for calibration?
So it might be good enough for calibration, but you still need completeness on the deep drilling fields at the end of the day. So that's also a part, right?
I mean, So I really think that some of the answer here lies in what is able to be done or could be done in terms of the low surface brightness and if there's problems there. So I don't know if we have anybody here who's gonna make a case for that, but anyway,
But then
I think
perhaps
this is
it's,
worth checking into. Yeah.
yeah, that's super valid. We can check into it. There is a lot of work on data management from the data management team and the Deep Drilling Fields Task Force to think about how to balance this. And we can certainly continue exploring it.
I certainly think that at this stage of the project where we don't actually have um, a super significant amount of existing coverage in these fields that we need to dither now. And the question might be, do we need to dither during the deep seasons when they get most of their visits? Okay. Let me go. There we go. So right. And now I'm going to talk about the Simone performance, which means the performance of the main telescope, Simone telescope. And here I'm specifically really talking about what's the visit gap performance. So up until v5.0, so any v4 or lower simulation, the Simone performance was modeled as, with our internal kinematic model for the telescope, as a 70% max speed TMA telescope mount assembly movement with a 3-second settle. So the max speed is the design 70% max speed is the design speed for moving the telescope around the sky. 100% is the maximum possible speed, but we never intended to move the telescope at 100% max speed. It was just there as like, in theory, you could do this, but in reality, we did not actually expect to ever move the telescope with 100% max speed. At v5.0, we switched to single snaps. And we also knew that the TMA performance might be a little problematic. And so we held back some of that performance. We actually went down from 70% max speed TMA down to a 40% max speed TMA movement, still with the 3-second settle. One thing to note is that most of our slews are very short, right? We go from one field to the adjacent field most of the time. So the TMA speed itself is not the bulk of the slew time. The bulk of the slew time is that settle. So even though we went from a 70% TMA to a 40% TMA, it wasn't a huge impact because most of the time is held in that settle. And when we said settle in this model, this was intended to represent necessary time after the TMA movement to achieve a fully settled, stable state. Now, what are we seeing at the summit? The current summit's performance is about they have split up these velocities and accelerations in altitude and azimuth a little bit differently than we had expected. And so there's now sort of a 20% of max speed in azimuth and 40% max speed in altitude. I hope I have that all right. Wait a minute. But it's split. So basically the summit is moving in azimuth and altitude at the same speed, and we expected them to move twice as fast in azimuth and not as fast in altitude. So in essentially there we can call this a summit 20% TMA movement. And then they have a variable additional overhead period. I won't say this is subtle because it's not all after the slew, some of it is before. So the additional overhead has varied throughout commissioning and early operations. And at some points, the median value per night was very close to 3 seconds, maybe 4 seconds. However, we have also seen it be close to 6 or 7 seconds on some nights, and it varies depending on a number of things that we're closing down on, and I think there is very clear room for improvement where people understand what the route for improvement is, but it's not there yet. And so this is an area of ongoing optimization. There are some known avenues for improvement. The exact solutions need to be tested, and in some cases, some software needs to be sped up. And it is possible that the end result of this is that we will have a this 20%, 40% TMA movement with more like a 1 second or 1.5 second settle, which actually wins overall compared to 40% plus 3 second settle. So if we get to the Summit 20 plus a 1.5 second settle, that's actually an improvement in our visit gap performance compared to what we have. It is possible we will end up there. We're definitely not there now. So the v5.3 simulations use this 20-40% TMA movement with a 3 second settle because on average that was looking like the best fit up until recently, and recently it's bounced around a little bit more. So this is optimistic at the start of the survey. It's pessimistic at some later date, but I don't know when that later date will be. So this is what we've used for the entire simulation. Now, the big changes in the final performance are actually coming from the updates in on-sky availability. So at v5.0, this is the second column here, we had planned maintenance time, which was only 2 weeks per year. And this was based off a very old estimate that came from very early in the construction project. And it is pretty clear this is outdated, not accurate, and we need to update it. So at v5.3, we have included an updated planned maintenance estimate that comes from talking to the people at the summit. And now, so instead of 2 weeks per year, we're now at 3 weeks per year, plus an additional 8 weeks in years 4 and 8. This may be a little conservative. So we'll see. The 8 weeks I do believe we'll need at least one of those, and I do believe we'll need 3 weeks per year. It is possible that one of those 8-week periods might be not necessary, but I don't know, and this is what I've been told is a good forecast, so we're going with this. We also have more planned engineering time. In v5.0, there was no other planned engineering time. In other words, if we needed a night of calibrations, we did not have that. The plan was to take calibrations in the daytime. This is not possible for the very faint, when we're getting the very faint flat field information we need. We can probably do that during weather, but because for the purposes of this simulation, we have not actually put it in only on bad weather nights. We've just said one night every 25 days throughout the rest of the survey, we will be off the sky. And this is in the survey configuration. This is set, like it's on a fixed 25-day schedule. So if that 25 days, or if that night happens to fall on bad weather night, then it doesn't have an impact for the overall survey strategy, but, or, you know, the same outputs, but it's there. The other thing is we also have added 2 half nights a week for the first 6 months. And this is like representing continuing work on image quality, for example. The unplanned downtime, so this is like things like faults or like something went wrong with the camera. This one's a little bit more complicated to explain because in v5.0, we did, and for quite a while now, we've had extra unplanned downtime in year 1. And in fact, the unplanned downtime we put into year 1 was worse at the start of the survey than we're actually doing now. But it ramped up to very good very quickly, and then it went into something that I think is unrealistically good. So in v5.3, we put in like multi-night downtime periods over 10 years that we did have in v5.0, but we've added those back into all years of the survey now. And then the shorter periods, like representing faults, we've started this out at about what we're seeing is probably close to the fault rate at the summit now, and then ramped that down more slowly and not ramped it down to nothing after 2 years. And then the weather downtime is the same. So this is the same as it was before. Okay. Are there any questions about this part? Because oh, we're all like almost out of time. But this is the major changes that we put into 5.3. Things we didn't include: lost visits due to poor image quality, or loss of depth in a particular image due to cloud extinction. And then here's the sort of the punchline for v5.1 or 5.3, sorry. We have 10% fewer visits overall than we do with 5.0. The changes, and that's due to the downtime primarily. The changes in the survey strategy drive small changes well, some changes in year one. We basically are more uniform across the whole sky due to the template tier. And we have slightly more visits in bluer bands in year one than we would otherwise. So these are basically skewing the filter balance bluer in year one. These are links. These are some other simulations you might look at. In particular, Comp Survey v5.3. This runs our 5.3 survey strategy, but with the old survey observatory performance, the old downtime, the old TMA performance. I'm going to leave the other things so we can talk about at the SEOC workshop. Fed already talked about math, but there are some links here if you want to go and learn a little bit more. And here's the SEOC workshop number 6, which I think Fed probably wanted to make sure everybody knew about. And that's it. If there are questions. We have 3 minutes. I'm sorry.
That's fine. We took some questions throughout and there were no raised hands, I think. Jeff, what do we do?
Did anyone have any more questions? We have a couple of minutes left before the top of the hour. If anyone wants to get in a question. Otherwise, note that the SCOC workshop is scheduled for next week, June 10th, 11th, and then one day the following week, the 15th, right? So coming soon. So if you're interested, do click the link. And I see a
Yes,
question
sorry,
from Tim.
Link in the chat.
It's in.
Super, thanks, Fed. Tim, question.
Hey Lynn, thank you once again for this, as always. Do you have a metric that sort of shows how quickly whether templates get built more quickly with the addition of this template tier of surveys?
Yeah, it is very difficult for us to predict when the templates will be built because we can predict when we think there will be enough images, but that also doesn't tell you exactly when the templates will really be built and available because it has to run through a bunch of additional pipelines that do take quite a while at the moment. And we don't, I think we're still iterating with data management on like what really are the image quality cutoffs and so on. My goal with the template tier is that we acquire this many visits or the visits suitable for templates within year one at all. Because the impact of losing 10% of our visits was we already only had about five or six visits per band in like U and G, which is too few to say that we can make templates out of. So basically, we were already scraping the bottom of the template requirements, even without including cuts on the image quality in U and G band. And so the template tier really is intended to try to make sure that we get enough visits and in good conditions. And for some of the band passes, that's not so much of an issue. We would have probably acquired that many in like R and I, for example. But in the bluer bands U and G, I think there was a real risk of us not actually acquiring the visits we needed for templates.
Okay, thank you very much, Fed and Lynn, and to all of you for attending. It is now 10 o'clock my time, time to wrap up. Do continue the conversation on the community forum if you have more questions that you would like to address. Otherwise, thanks for being here, and hopefully we'll see you at future science assemblies.